All right, so today, as Lance mentioned, we are going to talk about transport technologies. Of course, that's what we have been talking about in our series here. But today, what we're going to do is look at all of them, both individually and together, and kind of talk about why would I use one in one location versus another. Previous tech talks have been more about those technologies. And how they work, and there'll be a little bit of that in this presentation. But today, what we're going to do is kind of walk through if we were sitting in your boardroom and we had a whiteboard and we were kind of looking at your requirements, and then which technology would we pull out to address those requirements and why. So first of all, if you've been to any of these tech talks before, this will look familiar to you. And really, it's because this is where we have to start from. Everything ultimately has to be cost efficient. And when we are looking at network design and which application of technology we want to use, we have to consider first and foremost what the cost is going to be. And so my upside down triangle here, for those of you that haven't seen it before, if you look at the green double-sided arrow there, that's cost, meaning that the wider that layer is, the more money you're going to spend on it. And this is really independent of vendor. This is simply because of the nature of the beast, right? Routers cost more than switches, which cost more than optical equipment. So if we can move your traffic on a lower layer and still meet all your requirements, then overall that's going to be a more cost-efficient way to build a network. What you'll see in this presentation is that we can take multiple layers and put routers where they're appropriate, which is generally not everywhere, switches where they're appropriate, and then underneath it all, a very cost-effective and efficient transport design. So cost-efficient transport, always done at the lowest layer possible. We don't want to give up capabilities if we need them, but we certainly want to keep those costs in mind. And then what you'll see here is that it is very common to put a DWDM or an optical transport layer in as your foundational layer, and then to run switching and routing across that optical layer. But there are certainly applications where just layer 2 switches interconnected without an optical layer are appropriate. I've even deployed situations where every device was empowered as a layer 3 router. Those are rarer, and the requirements where you've got to have layer 3 everywhere are not real common in terms of a transport design. But the possibility remains, right? Those designs can certainly happen. All right, so again, right, we're visited by our friends Pink Floyd as a great example of how DWDM works, right? So this is a refresher for just about everybody, but for the new folks, this represents a glass prism. We have white light on the left-hand side, which is really just multiplexed wavelengths, right? There is no white light. White light is a combination of all frequencies, right? All visible frequencies. But then when you put it into a glass prism, each one of those wavelengths will diffract differently, and that's why you get a rainbow. Well, this is DWDM at its core, right? All DWDM is individual wavelengths that are precision designed so that they can multiplex together, and each one carries its own data like as a discrete wavelength, as a separate pair of fibers. but then you can multiplex them together over a single pair of fiber, and now I've got multiple wavelengths, in other words, multiple data streams over one pair of fiber. So we use this for fiber relief in areas where you've got, or locations where you've got plenty of fibers. Fiber is still a resource. Why waste it, right? So DWDM is inexpensive enough that it can be employed just about everywhere to good effect. So why DWDM, right? Well, cost effective, right? Remember my cost pyramid. It's the most cost effective way to move data. Briefly, what it doesn't do is any data manipulation, right? So I can't change VLAN tags. I can't put quality of service on it. My capability to reroute traffic is somewhat limited. So it's what some people call a dumb pipe, right? So it's literally light beams going down fiber. And so that limits us. That's why it's so inexpensive. But if you don't need those things, then that's why we turn it up. Okay, the other reason is because each one of those wavelengths can be virtually any bandwidth you want it to be. So we have lots of customers that are still running 10 gigabit. We're converting those as fast as we can to coherent light, 100 gig and larger per wavelength. But each wavelength can be anything from 10 gig to our newest transponder, which is 1.2 terabits per wavelength, right? So unbelievable scalability. And that's just on a single wavelength. A typical design will provide dozens of those wavelengths, and the number of wavelengths that we can provision for you really varies. It based on your topology, your physical fiber, how far we have to go, how much bandwidth we need to push. All of those get engineered into the design when we build it, but easily dozens and dozens of wavelengths. The other great thing is that once the system is built, that let's say we build a 48 channel solution, right? So think of a highway that's 48 lanes wide. Well, you don't need to use all of that if all you have is one truck, right? You're going to use one lane, right? So like my old diagram here, my first lambda, which is just the Greek letter that represents wavelength, okay? So my first channel, or lambda, might be running at 100 gig or 200 gig, right? When I'm ready, I can just, when I'm ready, I can just pop another wavelength on, right? And this is simply putting another precision DWDM optic in. In some cases, you need to put one more card in, but you're not really changing anything else. You're also not re-engineering the network. The network is engineered right up front. So when you need another wavelength, you just turn one on, right? And so on. We add another one, and maybe by this time you're ready for a 200 gig or even a 400 gig wavelength. And so on, right? Lambda 4, all the way up to 48. We even have 96 wavelength solutions. You can see how this will scale extremely fast to really massive amounts of bandwidth. Now, the great thing is that this is just simply preparing you for the next decade where our solution will be in place, right? When we put a DWDM solution in place, we have no concerns about that thing being in your environment for 10 years or even more, right? It's going to be doing great work 10 years from now. The other aspect of this is that once you put the network in, the only cost to you to turn up new wavelengths is literally the laser to turn them on, right? So, pluggables, SFPs, CFP2s, lots of different form factors for the lasers today, but that's all that's required. There's no additional licensing, there's no additional cost. The engineering, as I mentioned, is all done. So we simply will spec out the equipment that's required. usually just a pluggable optic on both ends of the service you want to turn up. Occasionally, it's a transponder or a muxponder card, and now you've got 2 wavelengths or 3 or 4 or 17, right? So it's pay as you grow, right? Only turn them up when you're ready. The other aspect of the optical layer or the DWDM layer is that it can be made, even though the pipes themselves are dumb, the system can provide a lot of useful intelligence as far as the signal health. So where I live out in the western United States, what we call the big square states, it is hours and hours from one location to another, right? And if you're having to roll a truck to the other side of Montana, then you've got a long day ahead of you, and obviously all of that is wasted time while the truck's trying to get there to figure out what's going on. So that's where signal health and fiber health monitoring can really help. And so the solution I'm describing is essentially fiber characterization, looking at optical amplification, transmit and receive levels, attenuation, dispersion compensation, things like that, right? As well as OTDR technology. So Ribbon supplies technology that can be installed in your network and can provide OTDR traces on demand in service anywhere in your environment. So there's no need to roll a truck with an OTDR handset and interrupt traffic or lose any further time. What we do is simply turn on that OTDR, or what you would do is turn on the OTDR from your management console and then take an OTDR shot. And it'll tell you right away if there's a break, if there's an error, if you're getting some type of reflection or what have you. So OTDR and then signal health or fiber characterization, both are in-service tools that obviously allow you from your desktop to diagnose and get a remedy on the way if someone gets crazy with a backhoe in your outside plant somewhere. And then finally, what you want to look for is in this modern era of management technology, you really need to be looking for what are called APIs, right? Application Programming Interfaces. So what these are, for those of you that don't know, these are software sockets, if you will, that allow developers, either the original manufacturer or other third-party manufacturers, to create hooks between your management software and, say, your billing software, right? So that the data you need out of your management software is easily transmitted to other pieces of software in your enterprise that can use it, right? So that interoperability key between your management system and other OSS or BSS solutions, pretty critical. So northbound APIs are simply those manager of managers or your OSS type solutions, your billing solutions, your customer management solution. Northbound is basically, imagine the management for your DWDM system or your network system. Northbound would be up. So those systems that you typically think of as needing to pull data out of the management system. A southbound API, by contrast, is the capability for the management system to access other either pieces of software or hardware, right? So they're both important. You typically don't find one without the other because it's part and parcel of the new architecture that a number of vendors are looking at these days. So north and southbound APIs equal interoperability and more capability as you begin to integrate your business software into communicating a holistic environment. And then finally, open client optics, right? So these obviously, I'm sure many of you are familiar and perhaps even buy from the pluggable laser SFP CFP2 warehouses. There are a number of them out on the net, and they give pretty good pricing, right? And so there's really no reason to be bound by optics that are keyed to the hardware, right? So you want a system that will allow you to use those third-party optics, or at the very least, if you're going to buy optics from your equipment manufacturer, and Ribbon sells optics, then you want to keep us honest, right? You want to say, look, I can buy these 1310 optics on the net, virtually the very same optics for X price. So you need to either match that or get close to it. And then alien wave support. So for those of you that have been in this presentation series before, you know that alien waves are simply wavelengths, DWDM wavelengths that originate on someone else's equipment. So if a competitor's equipment is attached to a Ribbon solution and is sending the Ribbon solution and an alien wave or a DWDM wave, then we consider that alien. By the same token, if we're sending a DWDM wave to that third-party solution, then they would consider us an alien. So it's just an industry term talking about a wavelength that comes from outside this vendor's equipment. So what you want is to look for a vendor that supports alien waves, right? Because it's very rare that you're going to end up with, say, for example, Ribbon from one end of your network to another, right? It's very common to have multiple vendors, perhaps not multiple DWDM vendors, but multiple vendors in the network. And so we consider alien wave support sort of working and playing well with others, right? Because the reality is you have a network that needs to interoperate, and we need to understand that and give you the tools to do it. Okay, so that's DWDM. Let's move on to layer 2 switching. Again, we're moving up that triangle, so it's a little more expensive here, but what you'll see is that it's just, there's more value here, right? You can do more with the data that you're transporting. So this is one of the key elements of layer 2 switching. The question that gets posed is, why would I put an Ethernet switch in my transport network, right, when DWDM can do it cheap? Well, your options to protect your services are much greater, right, and give you a lot more control and provide not only better protection, but faster protection and easier to administer, right? So MPLS TP is a subset, some would say a subset of MPLS. It's actually a standard all on its own. TP stands for Transport Profile. And essentially what this does, if we get away from the network speak, what this does is if I am moving data from site A to site D on my diagram here, and I've got a ring topology through other nodes, then what MPLS TP is going to allow me to do is set up a working path and a protect path. And the protect path is going to be administratively down. So it's live, it can be used, but we're not passing traffic that way. All the traffic is going from A to D through nodes F and E. Well, when a fault is declared, which according to the protocol typically happens within 10 milliseconds, then the traffic all switches over to protect, right? So for those of you from the Sonnet days, if this looks familiar, you are right on target. That's really what this was designed after, was to have set paths, deterministic paths, where I know exactly where my traffic is going and exactly where my protect path is going. And nail those up right at the beginning of turning that service up. So if there's ever a fault and it switches over, I know immediately what path my protect traffic is now running on. So very straightforward to implement. It can support not just simple rings like this, but different paths through a network. If you've got more of a partial or a full mesh type topology, it's utterly reliable and switches that traffic over sub 50 milliseconds. It is a tunneling technology, so if I build tunnels from A to D through F and E on one side and B and C on the other, then I can put multiple services in those tunnels. And so when the tunnel fails over, all of those services fail over, right? So very, very useful in terms of protecting traffic on your network. Again, this is a layer 2 switching technology. Traffic engineering. So this is where you have, say, multiple service offerings. So you've got a customer that is buying as an example, 2 gigabit service from you. And so you are providing, in this case, probably a 10 gig interface, but it is throttled in software down to 2 gig because that's what you're selling them. And maybe then you offer them the ability to burst up to 4 gig every once in a while, right? And then you can track that in the management software. So looking at my little stoplight diagram on the right-hand side, this is what we call a 2-rate 3-color bandwidth profile. So I can create these profiles really at any level of bandwidth permission. So in this particular example, I have a customer that is paying me for 2 gig with the ability to burst up to 4 gig, which means occasional high bandwidth usage, right? So this might be, an accounts payable. They upload everything from all their remote locations up to a hub site once a month. This might be a hospital pushing health records. It could be virtually anything, but the point here is that they are paying a rate that gives them 2 gig, and then they can burst up to 4 gig. Now, what happens when they go to over 4 gig? Well, if they literally are pushing that much data, then those packets are going to be dropped. Well, why would you do that? Because this is one way to oversubscribe your bandwidth and therefore increase your profitability, right? So this gives you the ability to manage the traffic on your network with bandwidth profiles on a per customer basis that gives you that real granularity. Now this is, I did it for simple purposes in terms of gigabit, right? But this granularity goes much lower than you probably will ever even use in terms of being able to meter that traffic out to your customers. So that's one way to increase the engineering capability over your individual customers. Instead of just sort of throwing everything out there and it's a winner take all, you can design a custom solution on a per customer basis. VLAN tagging, I kind of skipped over this one. VLAN tagging, if you're not aware, is a way to tag individual traffic coming out of a location for a customer or for a service type. So not uncommon to tag, say, voice traffic in one VLAN and data traffic in another VLAN. Well, why would I do that? Well, VLAN stands for Virtual Local Area Network. And so what you're doing there is in software, you are individually identifying and then isolating traffic. Now that I have, say, voice and data, I can do different things with those. I can, because voice is much more delay intolerant, I can move voice up in the priority stack, and I can move data, which has built-in retransmits and acknowledgments and so forth, and is much more delay tolerant. I can move that lower in the priority stack because people don't get irritated when it takes an extra 10 milliseconds for an email to come in, but they do if they're on a phone call, right, or watching a video stream, right? So VLAN tagging is a layer 2 technology. It's ubiquitous. Everybody uses it. Virtually everybody uses it. And it's simply the way to identify traffic and then be able to manage it on a per flow basis. Quality of service is, as I was talking about, the voice traffic being a higher priority and the data traffic being a lower priority. Quality of service is one way to handle that. You've got multiple queues, if you will. So think of a highway with an HOV lane or even a couple of HOV lanes. And then everybody else is sort of out in the mix, right? It has to fight traffic. So this quality of service allows you to identify that traffic that you want to provide a relatively easy path through the network for. So in other words, you want to give it the HOV lane access. That's quality of service, right? That's how that works. And of course, you can increase priority or decrease priority to make sure those customers are handled appropriately. Okay, moving on to layer 3 routing. So routers, as I've said in earlier presentations, routers are the most capable boxes out there. You can do virtually anything with a router, but the situations where you would want to are extremely rare because they're very expensive. They're very capable. They're very valuable. Where you need a router, you absolutely have to have a router. You can't put anything else in there. But all of that comes at a cost, right? So why routers? Why do we use routers? For you, a lot of you, this is going to be very rudimentary, so bear with me here as we get through the slide. But it comes down to how we move traffic today and how we identify the sites, not only in our network but out on the larger, the world internet. Right. So we use a protocol called IP, or Internet Protocol. Every device out there and every device in your network has an IP address, which is equivalent to a street address, right? So if I'm trying to hit a server somewhere, then I need to know its address, because it has, I'm going to ask a question, I'm going to make a request, and it's going to send me an answer, right? So fortunately, we don't, as humans, have to know any of these things, except for you administrators. But out on the net, we certainly don't need to know those IP addresses. There is another system, which is beyond the scope of this discussion and the time we have, but there's another system that allows all of those addresses to be found and then data to be forwarded appropriately. For now, suffice to say that we use Internet Protocol and we use IP addresses to identify ourselves as a node and multiple nodes, and then to figure out how we get from one location to another. Because the Internet is almost infinite in terms of its capabilities and its resiliency, because there are so many tens of thousands, hundreds of thousands, I'm not even sure how many there are these days, no doubt millions of devices out there, each one with its own address. Okay, so this is the system that we have today to deal with that big mesh network, and then of course your internal networks. We use routing protocols, right? A routing protocol is something that operates at layer 3, and the purpose of a routing protocol is simply to understand the map of the territory, right? How do I get from here to there, right? An analogy that works pretty well is your sat nav, Apple Maps, Google Maps, and so forth. It figures out, when you tell it where you want to go, it figures out how to get there and the fastest way to do that, right? That's what routing protocols do. Now, inevitably, there's going to be a change. A route's going to go down, a router's going to go down, a company may go out of business, somebody backhoes a fiber, you name it, right? And so the routing protocol detects those changes and then recalculates just like your sat nav. When there's a wreck in front of you, it will say recalculating, get off at the next exit, and then take a bypass to get around that error, right? Or that wreck on the highway. That's what a routing protocol is doing, right? It's simply, in my example on the right-hand side, I need to get from A to D. You can see there are multiple ways to get from A to D, right? And maybe the fastest way is that straight line, relatively straight line between A and D. But what if there's a break? What if one of those routers is being rebooted because somebody is updating their code? Well, then I got to find another path, right? And that's what routing protocols do for us. Okay, there's many routing protocols out there. Depending on which application and where you are, there are different protocols for different requirements. And then critically, routers that are all running the same protocol in the same area are cooperating with each other, right? So there are a number of algorithms, subroutines underneath a larger routing protocol that deal with how do I communicate with my neighbors, right? How do I deal with changes, and when do I recalculate my routes? So that's one critical element of why you need to put routers in. That's why every one of you that's building a network with a connection to the outside world has routers there, right? That's why. Not necessarily important to have those everywhere else in your network. Not only are they expensive, but they're overkill, right? You're not going to need all of this capability. And then finally, I kind of called out MPLS because it's a ubiquitous protocol. For our purposes today, we'll call it a routing protocol. It really isn't layer 2 or layer 3. It's kind of layer 2.5, but we'll just call it a routing protocol, right? And it does virtually everything that a routing protocol does. It creates paths through the network to switch traffic. Interestingly, whereas with layer 2, I have deterministic paths where I know exactly what route I'm going to take from one location to another. With MPLS and with routing protocols, the route from A to D may be completely different from the route from D to A, right? Because it's a dynamic environment, right? They may come back exactly the same way, but honestly, it's particularly on the internet, right? It's actually rare for that to happen. So MPLS is simply just another routing protocol for our purposes here that facilitates moving data in a changing dynamic environment. Here's a relatively new technology that's come along, Ethernet VPNs. I'm describing this under layer 3 routing, but EVPN itself is really kind of a layer 2 technology, but it relies upon, if you look at my middle bullet here, it relies upon IGP and BGP. These are gateway protocols, routing protocols. It relies upon a layer 3 technology to understand the map, right? So it's kind of a combination, layer 2, layer 3. The great thing about EVPN, as opposed to other types of technology that we use for resiliency in a network, is that I can operate it in an active mode, which means like for instance, with MPLS TP, my circle protection diagram with working at protect, right? What's happening on the working side is I'm moving traffic. What's happening on the protect side is that bandwidth is set aside, but not being used, right? It's only used when the working side fails, okay? And with an EVPN, I can move traffic on both my working and protect paths. Not only that, but I can load balance across them, right, if I need to. If one starts to get congested, then I can move traffic onto the other one, right? It supports a number of other really valuable technologies. Mac mobility. This is a simple example, is picking up your laptop and moving to another part of the campus, right? Your MAC address is a layer 2, think of it as a layer 2 IP address, right? It's a hardware address that is hard coded into your laptop, right? And actually every network device. And it's how the network finds your laptop when you're moving, say, across a college campus or a large industrial campus. So Mac Mobility allows you to move from one location to another, and the network can track you and still knows who you are, and you don't end up with a break in coverage. Fully interoperable with layer 2 networks. So if you have MPLS TP in part of your network, and then you've got an uplink, say, as you approach your border routers out to the internet, appropriate to put EVPN there, right? So fully interoperable there. It is a really a marvelous technology. Here's an example of how one customer deployed it. They had fiber to the prem equipment, their access equipment from a well-known vendor out in the hinterlands, right? Obviously, they're distributing the traffic out to their PON customers, but they wanted each one of those to have a redundant connection to the backbone, the distribution backbone. So instead of running a technology like 8032, which is somewhat obsolete by now, not as efficient, not as reliable, they wanted to operate EVPN here. So we set up EVPN on a per FTTP device basis, and gave it dual connections to the aggregation nodes that were then running layer 2 transport on the network. So again, you're able to load balance. It's active, and it is sub 50 millisecond to move traffic from one location to another. So very resilient, very useful, also very easy to configure. Configuring EVPN is really very, very straightforward. Okay, so we've kind of touched on the 3 technologies and why you would use them. Again, keep that cost in mind, right? It's always about cost. And then, of course, what do you need done? And is there a cheaper way to do it? So in summary here, layer 1 DWDM technology, the thing I'd like you to take away is very cost efficient, massively scalable on demand. Okay, so you choose when you want to turn up a new wavelength. All it costs you is the laser to plug in, right? And if you've already got a full transponder, then you'll have to put another transponder card in, right? But those are easy to come by. They're relatively inexpensive, and certainly inexpensive for the bandwidth that you can move. The other thing that I'll remind you of is that the DWDM wavelengths are completely independent of how much bandwidth you're putting on them. I can put a 10 gig wavelength out there right next to a 1.2 terabit wavelength. Not that I would, but you can do that, right? So that's just illustrating the point that the wavelength has nothing to do with how much data is moving across it. Ethernet switching, why do I do it? Because it gives me more engineering and protection capabilities on my traffic, right? I can aggregate traffic with Ethernet switching. So I can take multiple fractional 1 gig services and put them all onto a single 10 gig interface, and then keep them all separate in software, right, with VLANs or other technology. Protection switching, MPLS TP I mentioned, working in Protect, very reliable, very simple, relatively cost effective. Quality of service, being able to prioritize traffic, deprioritize traffic, putting bandwidth profiles on individual customers, which allows you to diversify your service offerings so that you can have, say, for instance, a gold, silver, and a bronze package. So if you've got somebody that wants high priority access through your network, you can grant that to them, obviously for a higher cost, right, to retrieve more revenue from your investment. Layer 3 routing. This is how we access the outside world. Occasionally, it's valuable inside of a network, but but those occasions are fairly rare. Usually, layer 3 routers go on the edge where your network is talking to the internet, right? Where people are trying to hit, Google and Netflix and data centers and so forth, right? That's where layer 3 routing typically is deployed in a transport network, rural or otherwise. It's used in the basic definitions of networks. One thing I'll point out is that every device in your network has an IP address because the network needs to know where all those devices are and what their addresses are. But that doesn't mean that those devices have to route at layer 3. So for instance, a layer 2 device, an Ethernet switch, or even an optical shelf will have an IP address because we need to know where that device is. But that device doesn't have to be a router. We just have to know how to get there. Okay, so there's about 3 more years worth of information we can go through on layer 3 routing, right? But for our purposes today, these are the high points and why you would use layer 3 routing where it is. Service protection as well. Nothing is more resilient than routers. They don't always do it sub 50 milliseconds. They don't always do it in a timely manner. But there is really nothing more resilient out there than the internet today because there are almost literally infinite paths to get from one location to another. So if 98% of the internet goes down, there's still going to be a way to get from one location to another. It's just going to take a while. And then finally, each of these, depending on what your application is, each of these might be what you're looking for as a standalone technology. We have many customers that deploy layer 1 technology and don't put switches or routers in for the transport part of the network, right? It's entirely a valid way to go about it if that's all you need, right? And the same with Ethernet switches. Okay, so finally, just sort of our 30-second infomercial here. So from a transport hardware and software standpoint, we are entirely standards-based. We don't do proprietary protocols. Everything is designed to be interoperable. And we have a lab down in Florida that is specifically for that purpose. So if you have a device that you want to know if it's going to work with ribbon equipment, then the chances are we've either tested it or we can test it for you. And we've done that with a number of you, existing customers. We are widely deployed around the world in over 140 countries, from telecom to utilities, critical industries, the defense establishments, governmental agencies. Some of the largest carriers in the world are operating on ribbon equipment with literally hundreds of millions of end subscribers. We don't charge persistent licensing fees for ribbon software. So once you've bought ribbon software, it's yours. We don't send you an invoice next year to relicense everything, right? It's one and done, which a lot of our customers appreciate. 100% US-based support down in Florida. For those of you that are considering or have applied for grants, when the government here in the United States hands money out, typically they will require that you are compliant with the Buy America Act, or there are other acts that are similar to that. This basically says if you're going to use taxpayer money, then you need to be buying from friendly companies and countries, right? So Buy America Act doesn't necessarily mean that the equipment is manufactured 100% here in the United States, but there are equivalents to America in terms of friendly countries, and these I'm sure will be familiar to you all. Canada, of course, Norway, Israel, the United Kingdom, Australia, those places, right? So we are 100% Buy America Act compliant. If there's a situation where you're needing that paperwork, we're happy to get on the phone with your USDA or your RUS rep and talk them through it, and we can provide that certification, that legal certification. And then finally, we continue to be fortunate and well planned, well positioned for delivery on our entire portfolio. Right, we're still delivering in a 10 to 12 week range. If you give us a heads up, and we know that a PO is coming, then sometimes we can even cut that down to a shorter period of time. So we are not having supply chain issues, I think, is the best way to sum that up. And then finally, a pitch. Those of you, I know a lot of you are already signed up for this. There are still some seats remaining for our tech forum, which is coming up the first week in November. It's going to be down in Dallas, Texas. November is actually quite nice in Dallas. And the venue is the Westin Galleria, which is a very nice hotel. It's attached to a big shopping mall. For those of you that might be interested in that, there's a skating rink, and it's a very nice venue. Golf. There's a golf outing on November 1st. The meat of the presentations, if you will, the core of the presentations are on the 2nd and 3rd. And then I think we feed you breakfast on Thursday morning on the 4th, and then on Voyage. So we're going to have a number of product demos existing, as well as future products that are coming out in the not too distant future. We will have a number of experts there. Drew, who is hiding behind the scenes here to answer your questions, may even be doing that as we speak, is going to be there. I'll be there, and a number of people that are much smarter than us. Our executives are going to be there as well. So if you want to buttonhole one of our executives and have a meetup with them, then we can certainly make that happen. Your registration link is there on the lower left, so grab a quick screen capture, and hopefully we'll see you there. And with that, Lance, I'll turn it back over to you.
All right, thank you, Jack. Also in the chat area, I believe Elizabeth put the dates and for the Ribbon Tech Forum along with the link. So you could also check that chat area and click that link and go straight there and check it out. So appreciate the time today, Jack, and the material. We did have a few questions come in sort of here at the end, maybe off some of your last set of slides there, but I thought I'd pose a couple of these to the audience and see if we can answer these. The US-based support that you had there on one of your bullets. Can you describe that a little more? What really is that? What does that entail?
Well, so I mentioned Florida a couple of times. So Florida is where our technical resources are based, down in Fort Lauderdale. That's where the lab is. That's where our action line, what we call the TAC, is based. That's where it's been based for decades now, and it's not going anywhere. So if you are looking, if you have a contract with us for support, then that's who you get, right? You will get somebody right there on the TAC line in the Fort Lauderdale office. One thing that's unique about it is that when you call, you're not going to get a dispatcher, or you won't go to a phone tree. You will go straight to an engineer. That engineer will be the person who deals with you all the way through your issue. If they have to pull in other resources from elsewhere in the TAC, or from tier 3 or tier 4, research and development, product management, whoever, they're still who you're dealing with, right? They will pull those people in as necessary, but it's all on them. We handle all of that for you and provide one person that you deal with, and one person accountable to you. Often what we'll do is once you have a Ribbon network up and running, there will be a designated engineer that is really your engineer. And then, of course, we'll usually have a backup or two in case they're out on vacation or what have you. But you'll pretty much call the same person every time. And there is a lot of additional paperwork. I don't have slides on it right here, but there's a lot of additional paperwork that goes in to documenting the network that we've sold you and installed for you and turned up for you, so that you have a full set of documentation at the end of the commissioning process, and we have a copy. So inevitably, when something goes wrong, you get a break, or a laser goes out or something, or something's been misconfigured, then you call us up. It's 3 o'clock in the morning. You have a map. We have a map. We're looking at exactly the same thing, and it really speeds that mean time to repair. Really shortens things. We do not roll support around the planet. It starts in Fort Lauderdale and it ends in Fort Lauderdale. I mentioned the lab as well. We have a lab there that is open to our customers if you want to do interoperability testing. If you want to come down and try out a configuration before you put it in your environment, then our lab is open to you, and there's no charge for that. Right, that's just a service we provide, and we find that not only do you benefit, but we benefit as well. So that's something that we like to do.
Very good. Thanks for that detail on the support. I know you mentioned Buy American Act and sort of why that's important with federal funding, and it doesn't necessarily mean that it's U.S. manufactured product, but there was a question about in more details around the Buy American Act. So I don't know if there's anything else you can add to that.
Yeah, so not really. That I think you will know if they are requiring Buy America Act compliance by virtue of the paperwork. A good rule of thumb is if you're getting money from them, like a grant, then that's pretty much what they're going to require. If you're just using RUS paperwork, the 395 form to use sort of the T's and C's, and you feel comfort in using that, then that generally doesn't require Buy America, right? And we do deals like that all the time, or designs like that all the time, right? The 395 form, the T's and C's that RUS put out they work really well, and we have no problem with them, right? So if you want to use that paperwork, that's fine. But generally, if you're using money from the government in one of the myriad of funding vehicles that are out there today, then typically you're going to need Buy America Act. On that note, for a lot of you, I'm going to be preaching to the choir, right? But there are so many funding vehicles today. This is once in a career type, once in a generation type environment that we're seeing, and it's great to see, because what we are thinking of it as this bridging the digital divide, bringing broadband out to the rural areas. It's very much akin to what the government did in the 1930s with rural electrification, right? We want lights on in every house, right? Well, the broadband is no longer a luxury, right? It's not just about streaming Netflix, right? It's about giving your kids access to the study resources that they need. It's about educating folks outside of primary, secondary school. It's also about telehealth, telemedicine, so many opportunities that rural areas typically have been left out of, whereas the urban areas have had the benefit of it for years now. So it's a very worthy endeavor. Like anything that the government does, it's kind of a 900-pound elephant, and so it's difficult to wrestle and get moving in the right direction. But we have a lot of experience with that, and so we're happy to help you negotiate and navigate through those pitfalls. So
great, thanks for that detail, Jack. And the last thing was on the delivery stuff. You mentioned supply chain in 10 to 12 weeks. I think I saw. How is Ribbon able to meet those type of deadlines, and why is everybody else taking longer?
Yeah, so great question. I will give credit where it's due, and that is that we started moving our supply chain out of the Far East and shortening that supply chain prior to the COVID asteroid impact, right, to the supply chain, global supply chains, right? Obviously, no one is ignorant of what has happened to supply chains. So we did start taking those steps before COVID even appeared on the world stage. But a lot of that's, I'll call it luck, right? I mean, we had that initiative not in advance or anticipating a COVID type event, but because it was good business at the time. And then COVID, of course, came along, and those that hadn't started moving their supply chains and finding alternate suppliers and so forth, obviously were adversely affected. So it's one of those things where we just, we crossed a railroad track right before a speeding train came by. We kept moving. We made the right decision to get across the tracks, but the fact that we didn't get hit by the train is there was some luck involved. And so that's how we're able to maintain that short time frame. Earlier this year, we were about 8 weeks. It has moved out to 10 to 12. But right now it's holding steady at 10 to 12. And I don't anticipate any changes to that anytime soon.
All right. That's good stuff. All right, everyone. Well, that's all we have for today. We have no more questions at this moment. We thank you for attending. We will be getting an email out later today with a replay of everything you heard today. So if you get that email and you have a question, feel free to reply and ask that question. We'll copy the slides to that as well. So just be on the lookout for that. And then again, we do have one more webinar in this series. It's next week. I believe it is also on Tuesday, or actually not next week. I'm sorry. It's the 27th of September. So 2 weeks away. So we look forward to you attending that one. And again, thanks for your time today. We will talk to you all soon. Have a great rest of your week.